Hello everyone, my name is Elodie Bouzbib and I'm a PhD student at Sorbonne University. I'm about to introduce CoVR, a novel robotic interface providing strong kinesthetic feedback in a room-scale VR arena that we developed with my supervisors Gilles, Sinan, Haliyo, and Pascal Frey. A main challenge in VR is the lack of convincing haptic feedback. It is common to use controllers. They may vibrate when we virtually touch a wall, for instance, but they do not constrain the users as they focus on the user's hands and they do not provide force feedback on the whole body. So eventually a user is more likely to go through the walls. This presentation aims at demonstrating that VR can benefit from large-scale force feedback, and it shows an interface that enables it. Hardware-wise, CoVR is a physical column mounted on a grounded XY Cartesian sailing robot that dynamically overlays multiple virtual objects. Software-wise, it predicts which object to overlay. For instance, here, the user is free to interact with any part of the wall with no regards to the scenario's progress. And when the user is moving, the system is moving accordingly to overlay the predicted part of the wall prior to interaction. Let's take a top view of the arena with CoVR here at the bottom right. First, to avoid CoVR going through the user when this latter is on its trajectory to reach an object of interest, we attached a virtual cone-shaped obstacle around the user so that CoVR naturally avoids it. In a non-deterministic scenario where multiple objects of interest are available, CoVR naturally moves at the barycenter of all the objects of interest positions. To be able to move, it is actually attracted to the different virtual objects with a spring damper model where their stiffnesses are converted into weights. The weights are a function of the user's HMD position and orientation. We evaluated our model in a technical evaluation to find the relative contribution of the distance over the orientation and to test CoVR's ability to physically overlay correct targets prior to the user interaction. When a weight is equal to 1, the object has been chosen. We found that the parameter is independent from the number of distractors in the scene and that the optimal one provided a little over 80% success rate in an entirely uncontrolled environment. This actually can be increased up to 95% with the scenario-based model when we add, for instance, 75% prior probability for the target to be interacted with among all the available objects. Now that we defined that CoVR allows for non-deterministic scenarios, let's define how to interact with CoVR. One of CoVR's key features is to have the capacity of resisting to body-scale user actions, such as pushing on rigid walls or even leaning on them or crunching under them or going into it. We create interactions on CoVR's panels made of cardboard, and users can explore the environment to find a haptic code. On CoVR's skeleton, we can mechanically attach props to enable directed manipulation, replicating here a slot machine. CoVR can also carry multiple potentially heavy objects, up to 80 kgs, that users can freely manipulate or make interact with each other. For instance, here, the user is freely manipulating a cube that does not physically fit in the locker. CoVR provides strong traction forces. For instance, it can act on the users by pulling them and leading them through forces, simulating traveling on a magic broom. But it also enables to literally transport the users. It also can physically initiate the interaction with the users. For instance, a fabric can slightly brush the user's head to simulate the crossing of a ghost. To sum it up, CoVR does not constrain the users to hold continuously a controller, and it actually encounters the users when an interaction is required. Whenever CoVR is static, it allows both bare hands exploration and manipulation with over 100 Newton per stiffness. And CoVR's key feature is to enable whole body interactions with large kinesthetic feedback, and these are even stronger whenever we take advantage of CoVR's displacements. We conducted a user evaluation for usability purposes and to find out the favorite interactions. In terms of usability, we didn't have any unwanted collision with the users or mismatches regarding their intentions. Large-scale kinesthetic feedback was appreciated, and being transported and led through large traction forces were the favorite interactions, gathering all the votes. We presented CoVR, a novel robotic interface, through its implementation and usability. Results show that VR can indeed benefit from large-scale force feedback. Thank you for watching this presentation.